Hi, welcome. Today going to continue our discussion of the K omega SST IDDES model. So in the last video we stopped here at stop short of discussing what this FD is. Now we're going to talk about this FE function, which is according to the paper, they call it the elevation function, which is to help take care of this log layer mismatch. So let's see if we can remember what FE is. FE is something like this inside the model. Okay, so there's FE2, there's some booster function here. I'd like to call it a booster function, but over here this thing isn't necessary, so there are some changes. Okay, I will copy and paste some of these here. Okay. Alright, so I'll copy and paste from the last time. Yeah, copy and paste and put it here, and then I'll say there are some changes to be made. Alright, so first I'll get rid of this, get rid of this. This is not important. Okay. Alright, so yeah, this is what we have. So I'll just tell you what is the difference between now for FE. I'll just tell you what the difference is. Alright, first this thing is taken out here because apparently I think the author thought it was kind of redundant, so we didn't quite need this. Plus anyway, this was meant for the Spalart omnibus model. These are based on Spalart omnibus model constants, so it doesn't quite apply here. So they took it out. Alright, next thing, FE1 remains the same. It's 2 times exponential minus 11.9 alpha square. If alpha is more than or equal to 0, alpha is this function here. Then if it's less than 0, it'll take this expression 2 times exponential minus 9 into alpha square. Alright, same thing as before. FE2 is still the same. Okay, FE2 is still the same here. 1 minus maximum FTFL. Again, FT and FL, they're the same as very similar form as the equation before. Alright, and the same as the equation before, in that yeah, they're the same as the equation before. You have this CT and CL here, and then you have RDT here and RDL here. All of these are just here to help you adjust for the log layer mismatch. For this, it's based on the length from the wall exclusively, because alpha square is a length from the wall kind of a function. For RDT, this is a turbulent viscosity kind of a function, so that's where it comes in. So RDL, RDT are very similar. Okay, they're very similar, though again we rewrite them as such. Remember, RDT is also appears here in FDT. Okay, so they use this FDT function over here. Though in this paper it is written slightly differently. Again, we use this in the denominator in place of this maximum blah 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 function. Okay, so we just replace it here like so, 1, 2, and 3, and then we don't have this maximum function anymore, so that's kind of redundant. This one I can just get rid of it, and that's what RD, RDL, and RDT is. So just do take note of the key changes. So this blending function for FE and this blending function FD tilde will make the length scale correct for IDDES. So that actually just sums up. This sums up the IDDES model for K omega SST. That's all. Okay, then of course there'll be some constants I mean, they're more or less the same as before. CT and yeah, CT and CL, they are, you know, you kind of got to yeah, give them some values, and the values are over here. CTCL, okay, I'll just copy and paste, cut and paste this table here. Okay, so CDT, you will see lots of constants here. CDT, CDT2, all right, CL, CW, for example, which you will find, where do you find CW? Okay, CW should be in the filter. Yeah, CW is here. CL and CT will be here. That's all your constants, and the values are as follows here. They are given in the paper. CW 0.15, CDT1 20, CDT2 3, CL 5, CT 1.87. So this thing here is kind of redundant. I'll get rid of it. Okay, so there are a few comments from the paper which are important to note. Okay, for DES, DDES, calibrating CDT 1 from 8 to 20 is very important. But for IDDES, okay, CDT1 doesn't really change much. Doesn't change results much from 8 to 20. But if you change it to 25, it's too high. So this actually gives a rough value of what CDT1 should be. These are just model constants. But leaving it at 20, I mean, of course, you want to change it. If you change it back to 8, they change the results marginally. But leaving it at 20 kind of produces very good results. And yeah, so these are some comments for that model. Okay, and in this model, we also have, I mean, in this paper, we also have a simplified version of IDDES for K omega SST. For K omega SST. So what the authors thought was, this FE function was kind of redundant. They thought that FE was kind of redundant because this function actually behaves more strongly in the Spalart omorous model as compared to the K omega SST model. This is to prevent the log layer mismatch. And so they thought, okay, let's simplify the whole thing by getting rid of it. All right. And so in the simplified model, the modification they made, okay, the modification they made was like so. They just got rid of this whole thing. Okay, they set FE to 0 and this whole thing just becomes 1. Okay, so in simplified K omega SST IDDES, this is what it will look like. You just have the FD functions and get rid of it. So they found that omitting FE does cause a stronger log layer mismatch in the developed channel flow, but effect is marginal according to the authors. So do download the paper, refer to figure 6 for the reference. Again, the download links will be available in the description. If you see, typically my videos will be here. You just press show more and you'll see all the relevant links over there. So that's where you'll find all these things, and you should be able to see the PDF here, download full text from ResearchGate. So that's what I'll put. Okay, yeah. So again, CDT is set to 20, everything else is the same. Okay, so they found out that technically you can omit FE, and this is called the Simplified IDDES model. All right, and okay, so now, I mean, after you know what DDES and IDDES are in the Spalart omorous case, jumping to K omega SST case is relatively trivial. I say relatively because I mean the model formulations are very similar. Just of course that you still have to test them, and the authors did test them very well and thoroughly across backstep flows, back-facing flows, and some what do you call it, channel flows as well. So you can take a look at the paper for more details. Alright, so let's see how all this is implemented in a real CFD code like OpenFoam. So in OpenFoam, remember you can take a look at these links here. The source code is over here. Alright, the source code is here in the DDES and the IDDES. So we can take a look at the DDES part, and you can see what's the typical value, right? So we can go to the source code. This is the IDDES source code. This is the DDES source code. Alright, this is the DDES source code, the C file, and you will find that okay, CD1, the default value is set at 20, as we were talking about before. CD2 was default. The default value was set at 3. The default value is set at 3, and I mean you can substitute in your own values, but don't really need to since all these are given. And yeah, so that's pretty much it for the DDES. For the IDDES, you can see that if you want to see whether they use FE, you can just press Ctrl F and you type in FE, and you'll see that the FE is here from line 139 to 144. This is where you find your FB functions and FE functions. You notice they're still there. They didn't use the simplified version. The simplified version was in line 147 to 154, but this is only like, you know, in the comments. They left it in the comments here. So they didn't use the simplified version of the K omega SST IDDES model. So I mean, whether you put it in or leave it out, it does not matter so much. But of course, leaving it in will suppress the log layer mismatch a little bit more. So I guess they just left it in anyhow. Okay, so that's how it was being done in there. So you can see that here, over here, there's the FV1, which is 2 times blah blah blah. There's the alpha and the power term here, and this is if it's like more than 0. This is if it's less than 0. Okay, so these are the summation terms here to kind of give you the complementary function. If it's more than 0, then you switch on this term. If it's less than 0, it is switching on this term here. FE2 is over here. Okay, so FE is equals to max blah blah blah. There is a psi here for some reason. Okay, then there's a FE2. Oh, okay, I think I know why there's a psi there. This was for the Spalart Omorous version. So that's why there's a psi, there's a psi here. Okay, you see there's a psi here in the FE2. Okay, we can go look for the correct one. Oh yes, okay. You'll find there's the simplified version here. Okay, you'll find the simplified version here, all in the comments as usual. It's the same as the Spalart Omorous C code. So yeah, this is not being used. CDT1 is 20. Okay, CDT1 is 20. Yeah, so pardon me, yeah, CDT1 is 20 here, CDT2 is 3, CL is 5, CT is 1.87. So these are the values that we discussed earlier. Nothing too different. Okay, so if you remember all these values here, okay, except for CW, which is 0.15, all of them are listed here. And let's see the LLES, the LES length scale. Okay, LES length scale will be, yeah, CDS and then times the delta. What's the delta? Okay, it will be here. One of the pieces of code dealing with delta. I won't go into that. All right. More importantly, we see that okay, this is right. Fe equals to max Fe minus 1 scalar of 0, which is just 0, times Fe2. Okay, just make sure that this 0 is a scalar, not a vector inside the C code. But anyway, Fe minus 1 and 0, you have a maximum of that, and then you multiply by Fe2. There is no psi. Psi is dropped out in the k omega SST IDDES model. So that's right. It lines up with the paper very nicely. And again, just to remind you, this simplified formulation is here, but it is not being used in the k omega SST IDDES model. Right. So this is how we find it in OpenFoam. Okay, it's in 147 to 154. Yeah. All right. And you can see the constants used over here, the default values, and you can see here also the default values for the DDES models. All right. So that sort of covers it for that sort of covers it for the k omega SST IDDES and DDES models. Very short presentation because we've gone through many of the concepts before, such as the model stress depletion, what have you. Remember, this is it doesn't have the Smalt-Gorinsky model inside this equation explicitly, but it's meant to reproduce Smalt-Gorinsky-like behavior in free shear flows, and either warm model LES or DDES behavior inside the boundary layer. So remember, it's a hybrid model. So k omega and k epsilon, you become the k omega SST in hybrid if you do it right. Then you combine that with LES to have a DES hybrid model. You combine that DES model with a delay function to get DDES to prevent warm model LES from coming in too early inside the boundary layer. Combine that with warm model LES, and then you get IDDES. So that's how all these models came about. It's just compound and tweaking of models as it goes along, and a lot of it is based on empirical functions. So hopefully that takes away a lot of the confusion that the math could just looking at the math and the formulas could really cause some confusion and cause some scare. But yeah, this is all that it is. Okay, so thanks for watching. Do leave a like and subscribe if you found this useful. I'll see you guys next time. Bye bye.